everyone. We need to talk a little bit about what happens when you do substitution and you're working on a definite integral, because something does happen. And I want you to be really careful about this. There's more than one way to get to the right answer, but there's a specific thing I'm going to be looking for you to do. So just make sure you pay attention to the way I work through these. Okay, so number 5, the first part is just a basic power function, so there's nothing too weird going on here. We would say, okay, I'm going to use a power rule, that's x to the third, and then I divide by the new power, and then I evaluate from 0 to 2, so x to the third is 8. Wow, brain fart for a minute. So 8 thirds minus 0 thirds is just 8 thirds. And graphically, if we think about what we just did, we started with the x squared function. And then from 0 to 2, so this is 2, 4, we accumulated all the area trapped underneath it. So that's what this means, right? So now I want to look at sort of a simple composition. All I've done here is replace the x with the x minus 2, but I've also got different endpoints. So according to, how do I want to do this? I think I just want to look at a graph even to try and get the idea across. So thinking about this, all we've done is shifted the graph to the right 2. So now, instead of having a vertex at the origin, the vertex is at 2. And instead of going through 2, 4, we shift it over 2, so it goes through 6, 4. And we're not asking for the area between 0 and 2 anymore. We're now asking for the area between 0 and 4. So just looking at the picture, it seems like I'm asking about the exact same area, and in fact I am, but we want to be thoughtful about this with substitution. When you do composition, sometimes it just moves the area around, but sometimes it will stretch or compress the area, and sometimes it'll do something more complicated. So with substitution, what we'd want to say is, okay, we're going to sub out the x minus 2. This is a nice simple one, du dx equals 1, which means du equals dx. And what that is telling me is that the composition that I've done, shifting to the right 2, in this case it's a transformation, it's a nice easy one, doesn't change the width of my rectangle, so that part is certainly not going to change the area. What you have to be really careful about, so now I've turned it into the integral of u squared du, is that when you change your variables, that's going to almost definitely change your limits of integration. But it's not a guessing game as to what your limits of integration would equate to, because you made a formula that says how u's and x's are related. So here, changing from u to x absolutely does make a difference. It's not just an arbitrary variable because we've defined a relationship between x and u. Okay, so if we want to find the bottom limit of integration, it used to be 2, but that was an x value. So we're just going to run that through our formula and say, okay, well, if x is 2, u is 0 at that exact same time, whatever you want to call it. And if x is 4, we plug that in. X is 4, u is 4 minus 2, so this is 0 to 2. So like we said, that's exactly the same. The integral from 0 to 2 of u squared du is the same as the integral from 0 to 2 of x squared dx. Those are the same thing. If we were trying to graph them, we graphed the one up above already. The only difference when we graphed y equals u squared would be that we'd label the axes differently. So we would have u and y, but it would be the exact same picture with the exact same area. So shifting graphs does not change the widths of rectangles. So if you also shift the endpoints, you can catch the exact same area. Okay, I want to do it once more with a transformation, and they're not all transformations, so it does get messier, but this kind of introduces the idea of what we're doing. When we try the integral from 0 to 1 of e to the x dx, That again is a nice basic function. The antiderivative of e to the x is e to the x, and then I just have to evaluate. So I get e to the 1 minus e to the 0. And if we're thinking about pictures, 0 to 1, so this crosses through 1. So it's going like this, and then 1 e, and we're looking for this little stretch of area right in here. Okay, so x, y. We are, in the second part of this problem, replacing the x with a 2x. So that's going to be our composition that we're looking at. This is another simple composition where we can say exactly what that does to the graph, I hope. If you multiply your x's by 2, that's actually going to make it increase or decrease, but in this case increase more quickly. So it's scrunching everything in. It's horizontal compression. If you cut your x values in half, you'd get the same y values from the original function. And we've also compressed our interval down, right? We were going 0 to 1, now we're going 0 to 1/2. So it seems like, other than the fact that this is now skinnier, we should still go through 1, and now we should go through 1/2 e. There's definitely a relationship between the area I started with and the area I'm talking about now, but it did get scrunched a little. So if we follow through the U substitution or W substitution, whatever you want to do, let's do W this time. You will replace the 2x, which means that your dW will be, dW dx will be 2. So your dW over 2 would be your dx. So this is going to turn into e to the w times dW over 2. And then we do have to change our limits of integration. So when we plug the 0 in, 0 was an x value. To find the corresponding w value, plug it in the formula. When x is 0, w is also 0. And then when we plug 1/2 in the formula, 2 times 1/2 is 1. So this is kind of nice. It's starting to look like what we had before. So this says that what we started with should be the same as 1/2 e to the w dw integrated from 0 to 1. And we already did the work for this one. E to the w dw, evaluate from 0 to 1, should give us e minus 1, exact same work as up above. But now we have this extra 1/2. So what this is telling me is that I do get kind of the same thing, but by compressing the graph, right here I can see it, by compressing the graph, I made my rectangles half as wide, so I'm only going to get half of the area I originally had. So like I said, they're not all simple enough that we can look at them as composition, as transformations, but the moral of the story is you can do substitution on definite integrals. It is extremely crucial. This is why, one of the reasons to see why it's so important that you replace your dx's with dw's when you substitute, and it's also extremely important that you change your limits of integration. So here's like the fancy version of what we just said. Basically, if you see one of these chain rule type things, you can substitute out the inner function. So, here, let me erase now that I scribbled all over it. The g becomes your u, g of x, which means g prime of x dx is your du. And then to replace your limits of integration, you'll just run them through the formula you made. You made a u equals g of x formula. Plug a in to get the lower limit, plug b in to get the upper limit. So might look a little crazy, but that really is what it's saying. All right, so again, be really careful with this. I specifically will want to see you change those limits of integration. Some people will just go through and do the integration and then change back to your original variable, which is fine, except there's some steps along the way where you're kind of contradicting yourself about whether you've got x values or w values in the limits of integration. So just make sure you can do it for me this way. Thanks for watching.